Okay, welcome back, everybody. Uh, I hope you can hear me well here. Is that everything is fine? So I just wanted to say something about the day today, and I wanted to wrap up the things which we didn't finish on Wednesday. So that's going to take some 5 minutes at most. Then the kind of plan is to give you a kind of overview of what we have done in this semester, and obviously also to discuss a little bit about the final project, which actually counts at 30%. The other thing which we wanted to just give you as an information is that we will meet again next week at our normal schedule. I have office hours also in the evening, and Julie put on Slack the office hours which she has. So I think in total we will have something like 10 hours next week when you can just reach out to us. And then if that's not enough, just shoot us an email, and then we can always set up a Zoom session. The other thing is that I'm going to send an email to everybody with all this information as well, so that you have it on as a regular email. The thing which I want to do now, just to sneak in some few minutes with trying to finalize what we did on Wednesday. In the slides and in the lecture notes, you will find much more material on Lagrangians. We won't have the time to cover everything, but you can look up these examples if you're interested. So let me try to wrap up the case we had on Monday, and then we're going to look at a kind of summary of what we did during the semester, and then we just move on to the solution of the final one. Feel free to serve yourself with cookies. So for me, it's something which I normally always do at the end of the semester, but we've had two years now with COVID. So this is actually 3 years since last time I did it. And that's a great pleasure to do so. Feel free. And then for those of you who wish to hang around, discuss the final, we have at least some carbohydrates which we can fuel up with if we get tired. Okay. So let's switch over to the whiteboard very quickly and try to wrap up what we did on Wednesday. And the case which we looked at Wednesday is one of these cases which we can actually solve analytically. And let me just quickly remind you of the kind of system. It's a simplified double oscillator, and you will encounter many such systems in different textbooks. You can have a double pendulum. You can have a pendulum with an oscillator. You can have a double pendulum like this one. And this is something which has been used to mimic the different molecules. In our case, this could be seen as a linear chain. And sometimes you can actually see that when you look at the structure of specific molecules, that the atoms align on a kind of straight line. That actually happens in nature, depends on the forces which are at play. In this case, what we did was simply to make a model where we had 2 oxygen atoms here and a carbon atom here. They had the same masses, which is actually not the case. And carbon is definitely not twice as heavy as oxygen. Actually, oxygen is heavier than carbon. But this is just a kind of idealization which we are making. And you could think of this as having a spring constant. And the thing you will often meet in physics, if you don't know anything about the forces, you can always assume that there is some kind of perturbation around a minimum. And if you have a small perturbation around the minimum, that often means a small oscillation. And then the system is just oscillating back and forth. And then you can approximate the forces or the potential with harmonic oscillator. So you would have a first derivative, which is 0 at the minimum. You have a small oscillation around the minimum. And that means that your potential energy is actually the second term in a Taylor expansion. That means the second derivative. And then you would have a constant, which you can fit to experimental data. So this would often be the simplest possible way you can approximate a physical system. So if you don't know anything, use the harmonic oscillator. Okay, so what we ended up with then, when we looked at the system was we defined coordinates x1, we had a coordinate x2 here, and then we had a final coordinate x3 for the final one. So this will be object 1, this will be object 2, and this will be object 3. And then when we did the different manipulations, what we actually did was to introduce a new variable, where we had this x, which was given by x1 plus 2 times x2 plus x3. So this is the central mass position. And then we defined a new variable, which we call for q1, which were given by x1 minus x2. And we had finally a new variable, q3, which was the same as x3 minus x2. Then we could rewrite this Lagrangian in terms of the following parts. So we had a kinetic energy and a potential energy. So we could rewrite it with some manipulations. So I'm just setting it up here. So q1 squared plus the q dot 3 squared. These are the velocities. We got a cross term, q1 dot q3 dot divided by 4. And then we had this central mass position, which was then given by x dot squared. And then when we apply the Euler-Lagrange equations, what we found then is that this linear, the central mass velocity is a constant, so linear momentum is constant. And then we had differential equations, which we got for q1, and that differential equation went like a 3 divided by 4 of m. So this is an equation where we have cross terms. So we don't have a set of equations which can be separated into one only with q1 and one only with q3. So that means that we can either solve numerically, obviously, we can always do it numerically, or if we are smart, we can find an analytical solution. But the types of systems with analytical solutions are not that many in physics or in science in general. But you can solve problems numerically to numerical precision. So if you don't find a paper and pencil solution, which you normally have for very few cases, where you can actually find an analytical solution or a closed form solution, this does not mean that you cannot solve a physics problem. And you can actually solve problems to numerical precision. So even if you cannot find the roots of a 10th-order polynomial, you can diagonalize a matrix, which is 10 by 10, and find all the eigenvalues to numerical precision. So the numerical approach is actually the more general one. But having analytical solutions is something which really helps, because then we can check the things we develop numerically. And you've seen examples of that throughout the semester. Okay, so what we could do now is simply to guess, and we know that these are oscillatory solutions because we don't have any damping, so we could guess on a solution of q1, which is given by a constant a times an exponential. We could take q3, which is given by a b of I omega t. We define these omegas as, or omega squared actually, as this k divided by the masses. So that's a typical scaling which we will do. And let's call this omega 0. And then we guess that there is a solution omega which doesn't need to be equal to omega 0. So you would have the omega 0 solution in case these equations could be separated. So q1 and q3 had their own expressions without any couplings between the two equations. Then this omega 0 would have given you the argument in this exponential function. Now, what you will do now is that we are going to look after the ratio of A over B. So we are going to plug that into the equations here. And what we end up with then is a simplified type of equation. So let me just bring that up here. So we can now take one of these equations if we take the equation for Q1, so if we take that one, so let's do that. And now we just plug in these solutions, and I take the second derivative for Q1. So that gives me minus 3 divided by 4. I get an A, and then I obviously get an I omega squared because I take the second derivative, and this is multiplied with E I omega t. Then I go back to the next term, which has the derivative with respect to Q3, and then I get a plus a equation which now goes like 1 over 4, and then I get again an I omega squared, and this is multiplied with a B of I omega t, and this is simply equal to minus K or omega 0, which we put in here, multiplied with A, multiplied with E of I omega t. And I'm just setting in the equations here. Now, in our case, we have 3 unknown quantities. I have A and B, and I have omega. So what you would do now is simply, obviously, to take away these terms. And now I'm going to divide by B, and then I compute I times omega squared. So I get 3 times 4 divided by 4, omega squared, A divided by B, and then I get minus 1 over 4, and then I have omega squared, and this is equal to, since I divide by B on both sides, then I'm getting minus omega squared of A divided by B. Now, what we are interested in is simply the ratio here. So this is an unknown quantity, and since we have these as constants, I can always set B equal to 1. There's nothing which hinders me because I'm looking at the ratio here. So when you do this, you can now find the equation here, and what you end up with as an equation, when you reshuffle a little bit, you get an A over B, which is equal to omega squared divided by 3 omega squared minus 4 times omega squared. And since you put B equal to 1, you can find A. And now you have to pick values. So you don't have enough equations to find an explicit expression for omega, A, and B. So you can now choose values. And you can choose a value of omega, which is equal to omega 0, for instance. If you do that, that means that you get A is equal to minus B. And then we're going to look at what this actually means. I could pick another choice here. I could say that omega is actually given by omega 0 times square root of 2. If I do that, then I'm going to get that A is equal to B. So what you would have to do now is simply to pick values and see what kind of solutions you get. So you don't have enough equations to determine exactly A and B and omega, but you're taking the ratios of A and B, and then you can fix the value for omega. So what does this actually mean? So if you go back to the slides, so let me just stop sharing this one, and then we take a look at the slides here. And we just move on a little bit. So there's a set of equations about the several examples here. We won't have the time to cover everything, but let's take a look at this specific example and try to understand what is going on in this specific case. So this is actually the same example which we've been going through. So when you do that and you pick these solutions, like you've seen here on the slides, what you would get then is that the first solution, that corresponds to the 2 outer masses moving in opposite directions. And they are synchronized with the middle mass being fixed. The second solution has both the outer masses moving in the same direction, but with the center mass moving opposite. And these 2 solutions are normally referred as something which is called normal modes, and they are characterized by their frequency and by the linear combinations of coordinates that oscillate together. Now, the reason why I'm bringing up this, without us doing too much with it, is that this topic of normal modes is something which you will encounter a little bit later in other physics courses. And in our case, since not everybody has taken a course in linear algebra, we are not going to dive deeper into it. But I just wanted to leave this as a kind of appetizer. When you go to more advanced physics courses, and you will encounter this type of discussions in terms of normal modes. So here we are just going to look at this as an example on how to use the Lagrangian formalism to actually find the equations of motions. And then we have done a pretty superficial analysis of the problem. And this is basically where we are going to stop when it comes to topics we cover here. There's more material in the textbook. There's also more material in the slides. And I invite you to take a look at it if you want to. If not, you're actually going to encounter many of these topics in later physics courses. And then you can always go back to Taylor's textbook and take a look at, for instance, these different topics in, I think it's in chapter 9 and 10, where they discuss different types of oscillations using the Lagrangian formalism. But this is a little bit beyond what we are going to cover. Now, one of the things I wanted to say a little bit before we dive into the final part, there's also an example of the double pendulum. This is one of the classic cases which you will often encounter in mechanics courses. And I invite you to just take a look at it, but we will not go into the details here. So let's now rather move to a kind of summary here. So let me just take a look here and say something about what we've done. So as you've probably seen, one of the nice things with COVID is actually that we don't have a final exam. If you look at that image, this is the way I felt before the exams. That's 1 week before. Procrastination was one of the hallmarks. And then 2 days before the exam, you start getting frustrated, there's desperation kicking in. And then after the exams, you were just done. I mean, I never remembered anything from the exam weeks. It was just a kind of total, blown out. So hopefully, with the kind of take-home final projects, you have more time to actually dive into what we have been doing and reflect a little bit more. And that brings me a little bit back to the philosophy of what we have been doing in the semester. So one thing, obviously, which we hope is that you feel that you'll be treated with respect. That's one thing, obviously. But another thing which is also important, and perhaps this is one of the fantastic things of being at a university, is the possibility to get new insights, to get new knowledge, new wisdom, or whatever. To me, the university years were perhaps some of the best time in my life. You met people which were thinking like you, like the same things. You could really absorb knowledge, digest it. So the thing which I really hope you felt you've been met with respect is your search for insights. That's something which matters to us. And us doing all this kind of computational exercises is not only because we want to give you these competences, but also because we think that allows you to dig a little bit deeper into the physics. That's the hope. Whether that's the case, we never know, right? So this is something we leave up to you to judge a little bit. And also we hope you had fun. Actually, this is a kind of preaching from my side. So being at university is a very important personal journey. To me, coming from a background where basically there were just poor farmers and working class people, it was not given that you actually would do a university degree. So some of us think of this as something which is granted, but it is not. So the enjoy, and it sounds almost like I'm getting pathetic now, but enjoy these years because these are fantastic years in your lives. So, and we obviously hope that the kind of search for knowledge which you thirst after is something you have felt has been treated well. I just wanted to give you a very quick kind of repeat of what we have done. I don't know if you can see this cartoon here. So we obviously hope that this is not the case, that you felt that you've just been digesting things and then everything just comes out. But actually there's been some reflection as well. And physics is actually about trying to understand nature. So it's not just swallowing knowledge, but it's actually trying to digest it, elaborate it, and then apply it to new cases. And one thing you will see in this final is that everything you have developed through the semester, in particular what you did in the second midterm, is something you can apply immediately to the second midterm, except that the potential and the forces are different. But as soon as you have decoded the forces, you can actually use the same codes which you developed for the midterm, and then analyze new physics. But at the same time, use the kind of insights you got when you looked at, for instance, a two-body problem, because this new two-body problem you're going to meet is not that different from other types of two-body problems. Actually, solving two-body problems is a pretty tricky thing. I've been so lucky that I've been together with my wife for almost 40 years, so we think we've been solving our own two-body problem, but many two-body problems are pretty difficult, actually. Not talking about three-body problems, four-body problems. Okay, so what we have done, or trying to do, and then you can look at this in a little bit retrospect and think of it. So we've been looking at equations of motion based on forces. We've been looking at forces, the work energy theorem, angular momentum, linear momentum. We try to cover various types of motion, from boring falling objects to two-body interactions. We've been looking at oscillations, harmonic oscillations, which play an important role in science. We've been looking at transformation of variables, which allow for analytical solutions. In particular, the two-body problem. Some of the forces which we encounter in nature, some of the fundamental forces, they are often of the type of central forces, and they depend basically on the absolute value of the relative distance between two objects. That leads also to important symmetries and important conservation laws. So if you have a force, like the gravitational force, then you know that angular momentum is conserved. And if it's not conserved, you've done something wrong. You will note that energy is conserved. And if energy is not conserved, you've also done something wrong. So you know from beforehand, without running any type of calculations, what you should get. So these are important things which you will encounter in many other physics courses. We've been looking at two-body scattering problems, a little bit superficial. You will encounter this when you do quantum mechanics a little bit later. We've been looking at variational calculus and Lagrangian formalism. And then we've been looking at deriving the equations of motions from a Lagrangian, as well as doing a Lagrangian with constraints. And the cute thing here with the Lagrangian formalism is that all these kind of exercises we did in the beginning of the semester with setting up the forces is something we can derive directly from the energy and the kinetic energy of the system and eventual constraints. And that's a pretty powerful formalism. We've been looking at how to solve these systems. We've been doing this by paper and pencil, which is an extremely useful exercise. But we've also been looking at algorithms for solving that. And the algorithms we've been looking at are typically Euler's method, Euler-Kromer, the velocity-Valais, which are energy-conserving algorithms. When we then look at, let's say, a type of motion with damping, where we have a friction term, then we have a non-energy conserving system. And then typically we would use the Runge-Kutta family of methods. We actually looked a little bit into integration methods when we derived the Runge-Kutta methods, but we haven't used that. Yeah, and basically, so you have essentially what you have is you have developed a basic one program to rule all physics cases. And the reason why I say that is not only because I'm obsessed with these Lord of the Rings movies, but essentially because you have a problem where what you need to do is to analyze the forces. So you are the one who is going to analyze the physics case. And when you can do it numerically, the only thing you need to do is actually to plug in the right forces. And then you integrate up velocities and positions. And then you have the motion or the dynamics, the time evolution of the system as a function of that specific force. And that's a very powerful way of looking at the kind of physics which you encounter in mechanics. Actually, when you do electromagnetism, you're also solving equations of motions, except that then you will often have electromagnetic forces at play. This is something you can easily do here with the codes which you have and the formalism you have studied, because you could just replace the Coulomb force, now the gravitational force, with a Coulomb force. And essentially, the only thing you would need to do is to change the physical constants. So the kind of overarching idea is that as soon as you have analyzed the forces at play, you can reuse your programs with new forces without having to recur to the few analytical cases which you can solve. So what we have at the end here actually is some of the learning outcomes which we have. I'm just going to put them up here, and you should feel free to take a look at it. And so when you look back at mechanics, you can look at these are kind of the ideal which we have, and then you can judge whether these kind of learning outcomes have been reached or not. And this is something which I will leave to you to think a little bit about. So typically when we teach and when we assess what you can, we're always trying to have some learning outcomes which we think are important. But you can take a look at that, and I'm not going to read everything here. So there are also competences and skills which we want you to have. So through the different midterms and weekly exercises, you have actually developed several algorithms and implemented them. So hopefully you feel that using Python now or programming language is something which can aid you in your understanding of a physics problem and in solving a physics problem. And then when you solve the problem, to analyze the problem and ask yourself, does this make sense or not? So these are also important kind of competences and skills which we obviously want you to carry with you when you now move into your third year or fourth year of studies. So I also have something about computations. And what I hope, and as I said, I'm not going to read everything here. The hope is that you see computing in a different perspectives. So computing the way I read it, that is solving scientific problems with all possible means. Not only paper and pencil, you have symbolic packages which you can use. So sometimes when you have solved an integral and you learn to solve integrals, it may not be so exciting to solve yet another integral. And then you could use something like a symbolic package like SymPy or Mathematica and solve the integrals, because I mean, there's not so much physics insights in solving an integral. So that means that when you are typically in a kind of a job-related situation or research-like situation, so I'm not solving integrals or complicated integrals. I would typically use Mathematica or symbolic package and find the solution and use that one in some kind of physics problems I'm dealing with. And this is the way you should think of these things as well. It's nice to be able to solve an integral or solve a differential equation, but if you can use these kind of symbolic packages and arrive at a deeper physics insight without spending, let's say, a day in finding the solution to an integral, I say that's an even better way of doing it, right? Because basically we know how to solve integrals, and there's not much more physics insight in that. So computations, the way you can think of it is actually solving scientific problems with all possible means. And it's you who has to judge which are the appropriate means. Yeah, you probably know my advocacy of procrastination. So we've kept a pretty lax attitude to deadlines, and that's because we cherish you developing your insights without being stressed too much. I think that's important for us. However, May 6 is actually a little bit mean deadline because we have to punch in the final grades on May 10. So unless you have a reason for an extension, we will try to be a little bit pickier with the deadlines. So as long as we can punch in the grades by May 10, that's the important deadline. But please do not go too much beyond May the 6th. So what else? Yeah, as I said here, so we have May 6th at midnight. Now, one thing which is always sad when the semester is over is actually that the semester is over, because you get to know new people. And I think both George and Abby and Julie and myself, it's been a great pleasure to meet you. So we want to wish you the very best. And I think just reading the different exercises and the midterms and everything you've handed in, it's been a great pleasure to get to meet you. So we are just wishing you the very best. I'm going to stop the recording, and then we can start looking at the finals. Or if somebody wants to discuss the homework 9 and homework 10, if you're not yet done, we can use the rest of the time to do that as well. Okay, guys. So I'm going to switch off the recording.